In this lecture, we are going to build on the previous lectures by using the conditional probabilities to find the probabilities of events for which we know conditional probabilities, but we don't know probability of this event. What we are going to do, we are going to talk about total probability formula. Think about a sure event, sample space, and think about n events. I denoted them with h1, h2 up to hn, which we call hypothesis. Notice that this hypothesis split the sample space, and sample space can be expressed as union of this hypothesis. However, the hypotheses do not overlap. So actually, the sample space is partitioned by this n hypothesis. The hypothesis I intersected with hypothesis j is an empty set of outcomes in possible event. So the hypotheses are exclusive. And think about now having an event A, and that event A intersects with this hypothesis. So event A could be represented as A intersection S. Well, S is the superset, so A intersected with something which is bigger than A remains A. But this superset S can be represented as the union of hypotheses. So we get A intersected with H1 union H2 union up to Hn. Simply that can be represented as union of this intersection, A with H1, A with H2, and union A with Hn. So think about this. This is A intersection H1, A H1. This is A H2, and so on and so forth. And this would be AHN. So simply event A is split as union of these non-overlapping events AHI. Now, these are exclusive. So when you take the probability of this event A, that is the sum of the probabilities of these exclusive events AH1, AH2 up to AHN. Event A and HIs are not independent. So to represent the probability of intersection, you go with general product formula. So probability of A intersection H1 is probability of A given H1 times probability H1 plus, and so on and so forth up to very end. Probability of A Hn is equal to the product P of A given Hn times probability of Hn. So this is what you see is the total probability formula. So probability of A can be split as a sum of these products, probability of A given Hi times probability of Hi. Why that is useful? Well, sometimes you may not know probability of A, but you do know probabilities of A if you know some hypothesis, under some particular hypothesis. And simply to find the probability of event A, you take weighted average of these conditional probabilities where the weights are probabilities of hypothesis. Of course, the weights sum up to 1 because the sample space is split completely by hypothesis, and the probability of A is simple weighted average of conditional probabilities. This is a very important formula of total probability. Now let's illustrate this by the example. Let's call it manufacturing base. And the story goes like this. You have the production of particular items in a factory, and only 3 types of machine produce that item, 1, 2, and 3. Now, the item could be conforming or not conforming. And machine 1 produces good item, conforming item with probability 0.94. Machine 2 produces good item with probability 0.95. And machine 3 produces good item with probability 0.97, as in table. Now, the volumes of production by these 3 machines are different. 30% of items are produced on machine 1, 50% on machine 2, and 20% on machine 3. So that is how the production is done and how the items are conforming. Then you have the production, total production, and you randomly select an item from the production. And the question is, if you don't know anything else, what is the probability that this item is conforming? So you don't have information on which machine is produced, and you are just interested in probability that randomly selected item from the whole production is conforming. If you knew what machine this item was produced on, you will know the probability. It will be 0.94, 0.95, or 0.97 depending on type of the machine. But you don't know. So you have to use total probability formula. You will take these conditional probabilities and weigh them by the production volume and get the probability of event A in this case. So as we start, we denote that HIs are the type of machine. The item is from ith machine. Are these HIs good hypotheses? Yes. The sample space is completely split by the three hypotheses because an item is produced only on these three machines. So it could be on first, second, or third. So the sample space is split as union of H1, H2, and H3. Are these events, hypotheses, exclusive? Yes. One item cannot be produced on two machines. It is produced on single machine. Do you know probabilities of these hypotheses? Yes, you do. Probability of hypothesis H1 is 0.3 because 30% of all items are produced on that machine. 0.5 for 2 and 0.2 for the third machine. One quick check if you selected hypothesis right is to check that sum of the probabilities of hypothesis is 1. The reason is the hypothesis split sample space and probability of sample space is equal to 1. Also, you have to make sure that hypotheses are not overlapping, that they cannot happen at the same time. So these are hypotheses. The event A that we are interested in is that item is conforming. And we do know the conditional probabilities. We know the conforming probability for machine 1, for machine 2, and for machine 3. These are given. Now, by total probability that randomly selected item without information from which machine was selected is conforming is total probability formula. And in this case, when you apply this, is 0.957. So if you select item at random, probability that that item would be conforming would be 95.7%. Another example that is interesting is the following. We need to find the probability that this circuit, let's call it bridge circuit, is working. Now, when you look at this circuit, there is something which is not the same as the circuit that we did before. The element A5 is bridging the two branches. It cannot be considered to be serial. It cannot be considered to be parallel. And it is simply messing up our analysis that we got used to in the previous example. So what we do in this case, there are many ways to solve this problem, but one way that uses a total probability formula would be the following. You place two hypotheses that element A5 is working, that would be your hypothesis H1, and that element A5 is failing, that would be your hypothesis H2. Of course, they are hypotheses. They sum up, the probabilities are given to you, 0.6 for working and 0.4 for failing in the table. Do they split sample space? Yes. A5 can work or fail. There is no third option. Are these valid hypotheses? Yes, they are. Let's take a look what happens with the circuit under these hypotheses. If hypothesis 1 is true, if A1 is working, take a look how the circuit looks like. It has these two serial connection with these two parallel things, A1 and A3, serially connected with A2, A4. And then we simply find the probability. Now, I am doing this quite quickly. Take a look at the solution. For the first two, 1 and 3, A1 and A3, I take 1 minus Q1 and Q3 because it is parallel and I'm looking at the probabilities of failing. But then I return back to the probability of working for that subsystem, and this is 1 minus Q1 and Q3. The same for A2, A4, the probability of working is 1 minus Q2, Q4. But then I take product of the two because these two are connected in a serial connection, and I need product of probabilities that these components are working. And in this case, I get that this is 0.8536, that this system under H1, when component A5 is working. Now take a look at the probability of system working if hypothesis H2 is true. That one is splits to the parallel connection of two inline connections, A1 and A2, and A3 and A4. So what I do first, I find for upper branch P1, P2 is working, and for lower branch P3, P4 is working. But then I switch to probabilities of them failing. 1 minus P1, P2 and 1 minus P3, P4, because I have parallel connection between A1, A2 and A3, A4. And multiplying these probabilities of failing, I get that this parallel connection fails. So 1 minus P1, P2 times 1 minus P3, P4 is probability that this system S is failing. And then I take 1 minus that finally to find that this system is working. And when I do algebra, the result is 0.7984. So by total probability formula, I get, in the first case, it is 85.36% times the probability that A5 is working, which is probability of hypothesis H1.6, and plus the second conditional probability when event A5 is failing times probability of element A5 failing. So the probability that this circuit is working is 83.15%. So in this unit, we saw the total probability formula, and we illustrated total probability formulas on two examples, manufacturing base and the bridge circuit. Thank you.